Hello, everyone. This is Jen Termel, and this is our final chapter for Chemistry for Engineers at Southern Maine Community College. And we're going to be looking at Chapter 9, which is Energy and Chemistry, or specifically Thermochemistry, out of our book Chemistry for Engineering Students, fourth edition by Brown and Holm. All right, let's get started. All right, so here we are on slide 2, and here we're looking at energy, and we're going to be focusing on two different kinds of energy in this particular section. First, we have potential energy, and potential energy is the energy due to the relative position or composition of an object. And then we have kinetic energy, which is our energy due to motion or energy in motion. And so now we have the equation for kinetic energy, which gives us 1/2 mv squared, where m is our mass in kilograms right here. Okay. And v is velocity in meters per second. Okay. So if you're working a problem and you're in grams, you have to convert to kilograms. And then if you are not in meters per second, you have to convert to meters per second. Okay. And we're going to be looking at energy in terms of joules, and that'll come in a little bit later when we look at that. Okay. Okay. So now let's take a look at heat and work, and they fit into thermochemistry. Um, and we're going to look at both of them. So heat and work are not state functions, whereas energy and enthalpy are. And so that they're a little bit more simplistic. And so what we're looking at here is, first of all, heat is the flow of energy between two objects because of a difference in temperature. And we always say that heat flows, the cold doesn't flow, heat flows. So heat will always flow from the warmer object to the cooler object. And the thing to remember is that if these two things are together, you're going to you're going to eventually get to the point where you are at equilibrium, and the final temperature for each object will be the same. And that'll be really important later when we're looking at calorimetry. And then next we have work, and work is the transfer of energy accomplished by a force moving a mass against some distance, or mass some distance against a resistance. So that resistance can be a variety of different things when we're looking through that. Now let's take a look at our units. First of all, we have the unit that's the joule. This is the SI unit of energy, and 1,000 joules is equal to 1 kilojoule. And this is a little bit from that previous slide. A joule, the units for a joule is a kilogram meters squared per second squared, which is why we had that meters per second in the kilograms in the previous slide. We have a couple of other calories here. We have the BTU, and the BTU is the energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And if you need to convert your BTUs, 1 BTU is equal to 1,055 joules. And then the next piece here is that 1 calorie is the energy required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. And so this is basically by 1 degree Celsius. Okay. And this is at 4.184 joules is equal to 1 calorie. For those of you that have had physics recently, physics often uses 4.186, and that's just because joules per gram degree Celsius. And basically, that's just because that's where they were using a different temperature when they originally went from 1 degree Celsius instead of 4.184. So it's a little bit different there. Okay. But here in chemistry, we tend to use this one. And now the big thing to remember is that food calories are actually kilocalories. And so if you see 1,000 calories of energy is equal to 1 kcal or 1 calorie, you'll see on food packaging it's with a capital, and so this is for food. So you want to remember that particular difference there. All right. So now we have energy transformation. So the thing to remember here is that the total energy remains constant. Okay. And so what that means is that energy in and to any system has to equal the energy out. And that has to really be balanced. So we have some phrases here that we're going to be learning. The first one is the term system. The system is the part of the universe being considered. Okay. And then next we have the surroundings, and the surroundings are the remainder of the universe, but primarily things that are close to the system. Okay. And so let's take a look at some examples of what that might mean. All right. So it says to define the system and surroundings for the following. So first of all, for water condensing on a pipe, then let's define, in this case, we'll define the system as the water because that's what we're looking at here. And when the water condenses on the pipe, then if the system is the water, then the surroundings for this are the pipe, the air right next to the pipe, um, perhaps the building that you're in, any other objects near the pipe, and that kind of thing. All right, now let's go ahead and take a look at our next one. We have burning coal. And so when we're burning anything, so we'll come over here, burning anything, our system is always the fuel and oxygen gas. Okay, so that means that when we're burning coal, our system is going to be the coal and oxygen gas because those are our reactants. Okay. And the surroundings are whatever you're burning around the coal. So perhaps that's the furnace itself. It's whatever you're attempting to heat. We'll actually say whatever you are attempting to heat. And so that could be maybe you have a coal burner in your house or for camping or wherever you're burning it. But whatever you are attempting to heat is also part of your surroundings. And then last but not least, down here, we have baking a cake. If we were baking a cake, then our system is the cake ingredients. Think reactants. Okay, so some of the ingredients and the surroundings would be the pan, the cake pan, and the oven, and the air in the oven, perhaps the rest of the house. Okay, so that's sort of how you differentiate systems and surroundings. Right. So now what we're doing is we're going to look at energy, heat, and work and how those kind of come together. We're looking at energy transformations and conservation of energy in this section. And the thing to remember here as we're working through this is that delta means change in. Okay, so whenever you see this triangle symbol here, whenever you see this triangle symbol, sorry, working on some things. Okay, this triangle symbol is the Greek capital letter delta, and it means change in, and it's always going to be your final conditions minus your initial conditions. Okay, Q, this is a little hard to see here, but if this helps, this is a lowercase q, and you might think about it like that. Q is heat, and its units are in joules. And W is work in joules. I'm going to make this Q look more like a Q. You can't do that on the computer. There you go. And then our delta E or so E final minus E initial, those are pretty hard to come up with. So we talk about delta E as being combination of our Q value plus W. Okay. And again, in this case, then our units are going to be in joules. Let's take a look at 7 here, and we're still looking at those energy transformations. And some of the important things to remember in this chapter is that you are often going to have to be really putting down your signs. So it might not necessarily say, it might say that we release a certain amount of energy. So if we're releasing a certain amount of energy, then what we need to remember here is that Q is negative and delta E is negative. If we're absorbing a certain amount of energy, then those signs are positive for Q and positive for delta E. If we are looking at work done by the system on the surroundings, then work is negative. Another example of looking at this when it says work done by the system on the surroundings, this exists when you have a gas expanding against a pressure. Okay. And then it says work done by the surroundings on the system will get a work value that is positive, and this is a gas that's being compressed by the surroundings. Okay, gas being compressed by surroundings. Okay, so you always have to think about who's doing the work or what's doing the work in that case. All right, so let's take a look at this a little bit. And here you can see down here that it tells us our problem here that says if 515 joules of heat is added to a gas that does 218 joules of work. Okay, so the gas is doing 218 joules of work as a result. And here we have 515 joules of heat added, and they want to know what's the change in energy of the system. So our first step here is to assign signs. Okay, so Q here tells us that we have 515 joules of heat added because we're adding it. This is a positive 515 joules. And then it says that the gas does 218 joules of work. So that means that the system, if the gas is doing the work, then that's the system doing the work. Okay. And so W is going to be equal to negative 218 joules. Okay. So now we can put that together and we end up with a delta E value equal to Q plus W. Okay. And our Q value is a positive 515 joules. And our W is a negative 218 joules. Okay. And working through this on the calculator, we will get 297 joules. All right. For many of you, remember this is the last chapter that we are doing, and I encourage you to pause the video recording and do these calculations yourself, mainly so that you are very familiar with working through them, so that you can work through them on your homework, but also so that you can work through them on a test. We don't want any calculator malfunctions during the final exam for this semester. All right. So now let's take a look at our first law of thermodynamics. Okay, so the first law of thermodynamics states that energy can be transformed from one form to another, but cannot be created or destroyed. You will also see the first law of thermodynamics called the law of conservation of energy. Okay, these are two words for the same thing. Okay, and the thing to remember here is that the change in energy of our universe has to equal the change in energy of the surroundings plus the change in energy of the system, and um, and that will be zero. So another way of looking at that is that delta E of your surroundings is equal to the negative of delta E of your system. And we'll be using that in the lab as well. All right, so here is a few forms of energy that we have. We have chemical energy, electrical, mechanical energy, radiant energy, thermal energy, sound energy, elastic energy, nuclear energy, and gravitational energy. In chemistry, most of what we're focusing on is thermochemistry, which is heat-based. And how that relates to chemical energy. So we're sort of combining those two pieces. So now let's take a look at calorimetry. And calorimetry is the method for measuring the flow of heat. Okay. And we're going to be doing two different labs on calorimetry. And the factors that affect our flow of heat are one of two things. We could either have our mass in grams, or we could have N for moles. Okay. And the big thing to remember this is if we're converting, because a lot of times we'll have to do that. Let's say that we need to convert mass to moles. Okay, if we need to convert mass to moles, then we do that by doing the mass of our object, our mass in grams specifically, divided by your molar mass will equal your N moles, or your number of moles. And then if we're going in the other direction, if we're going from moles to mass, then what you could do is you could take your number of moles, N of moles, okay, and we're going to multiply that by our molar mass, and that will give you your mass in grams of your compound or element, okay? The next piece that we're going to be working at is specific heat. So we have a couple different things in there, but the type of material can be used by either a lowercase s or a lowercase s or a lowercase c. Okay, if you see one of these two things, then you're talking about specific heat capacity. And specific heat capacity, we'll define these actually on the next slide. And then the other option here is the molar heat capacity. And the thing to remember going forward is that delta T is equal to T final minus T initial. And when we were doing gases, remember we always had to convert our temperature to kelvins. But when we're doing energy, we can be doing our temperatures here in Celsius or Kelvin. You don't have to convert specifically to Kelvin. Usually it'll be in Celsius and you can just leave it there. Okay. Now let's take a look at heat capacity and calorimetry a little bit more specifically, and let's define these. So we have our specific heat capacity or specific heat, and this is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay. Now for water, this is 1 calorie or 4.184 joules. And so you'll see the specific heat of H2O like this would be reported as 4.184, and the units for that are joules per gram degree Celsius, just like so. Okay. All right. And all right, so next we have molar heat capacity, and this is the amount of heat required to raise the temperature of 1 mole. So here we had 1 gram, and now we have 1 mole of a substance by 1 degree Celsius. Okay, and so the units for this are going to be, so CP, our molar heat capacity, is going to have units of joules per gram degree Celsius. And it can also be in Kelvin. So this is the same as saying joule. Oh, sorry. Joules per mole degree Celsius. Or you could list it as joules per mole Kelvin. The same thing up here. The specific heat, for example, of water would be 4.184 joules per gram degree Celsius, or 4.184 joules per gram Kelvin. And you're just remembering that because Kelvin in Celsius, the increment is exactly the same. Okay, so both specific capacity and molar heat capacity are specific to two things. One is the compound, and the other one is the phase it's in. And by phase, we mean solid, liquid, and gas. Okay. All right. So those three things. And specific heat capacity is different for, say, liquid water and solid water or ice. So you always have to pay close attention to which one you're working in. So let's take a look here. We've got calculating heat, and you have a couple things here. You have some equations that we're working on. And again, this is Q. So you can think about this in terms of it. It might help to see it looking a little bit more like a Q. There we go. So Q is equal to MC delta T. Some people will say MCAT. You're also going to see this listed as MS delta T. Okay, sometimes in the lab. Remember that S and C are the same thing. These are both your specific heat capacities. So specific heat capacity could also be a lowercase s. N, where we have, so M is your mass of your compound in grams. Okay, so this is mass of your compound in grams. This S or C is always going to be joules per gram degree Celsius, and temperature will usually be in Celsius. And then when we're doing Q in this case, then you have moles. And then this is your molar heat capacity, which is going to be joules per mole Celsius. And your change in temperature, again, in Celsius. And just remember that delta T is equal to T final minus T initial, or you might see T2 minus T1, either way. So these are the specific heat capacities and the molar heat capacities. And just as a quick reference for these, you have them here and you probably need them going forward. On a test, I would give you this information. So you do not need to put on your cheat sheet. Okay, this would be information given. And I'm always going to be using this would be 4.184. I'll always be using that all the way out, and usually I'll be giving you more of that. So a really big important thing here is that specific heat and molar heat capacities are always determined through experimentation. Okay, so we find these through experimentation, and they are constants. And as you can see here, solid water is 2.09, liquid water is 4.184, and then gaseous water is 2.03. And so it'll matter what state you're in, and we'll be working on those a lot. And then just as a review here for our units, you're going to see this more as, in this case, joules per gram Kelvin. And in this case, you would see it listed as joules per mole Kelvin. And remember, Kelvin's degrees Celsius are going to be the same thing. Let's take a look at a couple of these. And all right. So first of all, it gives us a couple of pieces of information here. It says that the molar heat capacity, okay, that's good to know. So that's CP, of liquid water is 75.3 joules per mole Kelvin. If 37.5 grams of water is cooled from 42 degrees Celsius to 7 degrees Celsius, what is our Q value of water? Okay, so here we have molar heat capacity in grams. So if we're dealing with molar heat capacity, then step one is going to be to convert this to moles. Okay, and just as a review here, we have 37.5 grams of H2O. And now we need to set this up to convert to moles. So we'll set it up to cancel our grams H2O and grams H2O. And this is going to be our molar mass. Let's put this in here. This is our molar mass here. And the molar mass of water, you hopefully can all find this, but it would be 1 oxygen and 2 hydrogens, okay, which is equal to 18.015 grams of water per mole. So now here we have 37.5 divided by 18.015. We have 3 significant figures, so this becomes 2.08 moles of water. All right, now that was our step one. Now our step two is to calculate our Q value. So remember that Q is equal to the number of moles times the molar heat capacity times our delta T value, okay, from the previous, a couple slides ago. And so that would be that 2.08 value that we used right here. We're going to plug that in right there. Times our molar heat capacity, which is 75.3, right? Times our change in temperature. And remember that it's T final minus T initial, which means that it's 7.0 minus 42.0. Okay? Remember our order of operations, you have to do what's in the parentheses first. Okay, and 7 minus 42 gives us a negative 35 degrees Celsius. And then when we calculate this all the way through, we will get negative 5,482 joules. And if we are pausing this for significant figures, so even though you have this 7.0 right here, when you do this, use adding and subtracting rule. So now we have 3 significant figures all the way through. And so if we are moving to significant figures, this becomes negative 5,480 joules. You can't just leave off that last 2. I would rather have you give me 1 extra significant figure and report the 5,482 than to round too much. So please don't get in the habit of rounding too much, basically. All right, now this one is a little bit different. This one is, we're working now on the specific heat. It's and that's because on the previous slide, okay, if you look back up to slide, I think it is slide 12, you saw that it said that if we had solid aluminum, that the specific heat for that was 0.900, and that's joules per gram degree Celsius. Okay, and that's, you have that chart right above as well. Okay, and so now we actually only have 1 step. And so we're going to say Q is equal to M little c delta T. And again, that's the mass of our aluminum times the specific heat of our aluminum times the change in temperature of our aluminum. Okay. And the mass that we're dealing with there is 24 grams. And the specific heat is 0.9. And then our change in temperature. So now it says that we are raising its temperature by 15 degrees Celsius. So that means that delta T is equal to plus 15 degrees. So we can put that in right here. So times 15. And when we calculate this all the way through, you will get 324 joules. Okay. All right, now let's take a look at calorimetry. Okay, so here we have heat flow is measured by using a calorimeter, and we're going to be using a coffee cup calorimeter to do both an endothermic exothermic reaction and to do a Hess's law reaction. Okay, a calorimeter measures the heat evolved or absorbed by the system of interest by measuring the temperature change in the surroundings. So what we're going to need to remember here is remember that Q of the system is equal to the negative Q of the surroundings, okay? And that Q gained is equal to the opposite or negative of Q lost. All right, so let's take a quick, just don't forget these negative signs. These will be pretty important going through. All right, so let's see how we would use this. Okay. So here we are in slide 15, and it says that we have 450 grams of cold water at 5.55 degrees Celsius and a 125 gram sample of copper at 98.6 degrees Celsius. And we want to know what's the final temperature. Okay, so a couple things again from that previous slide. Let's make a little list of what we know. So what we're looking at here is we're going to mix these. So we have hot copper and cold water. So that means that the Q value of the water is going to be equal to the opposite of the Q value of the copper. Okay, so let's kind of make a list of what we have for that. First of all, so the mass of our water is equal to 450 grams. And the specific heat of our water is equal to 4.184 joules per gram degree Celsius. And our delta T is going to be equal to T final minus this initial value, or 5.55 degrees Celsius. And now let's take a look at our copper. So the mass of our copper is equal to 125 grams. And the specific heat of our copper, this was again on that previous slide. It's something that I would give you if it's not on a slide, but that is 0.385 joules per gram degree Celsius. And the change in temperature of our copper is going to be T final minus our initial one here of 98.6. Okay, so now what we can do is we can set this equal to each other. Okay, so what we would do is we should say, because Q is equal to MC delta T, we set all of these, and just here, I'll just kind of put that up here. Remember that Q is equal to MC delta T. Okay, so first of all, the mass of our water is 450 grams times the specific heat of our water of 4.184 times the change in temperature, which is T final minus 5.55 equals, now don't forget this negative sign, negative, and then we have 125 grams for our copper and 0.385 for our specific heat, and then our T final minus 98.6 for our delta T. Okay, so now what we need to do is we need to bring this through. So let's remember our rules for distributing, okay? So our rules for distributing, take the 450 and the 4.184, and you're going to take this and you're going to multiply it by TF and by negative 5.55. And the same thing here, you're going to take these two values together and you're going to multiply by both of them. If you haven't done this kind of math in a long time, this is called the distributive property. Okay, so what we end up getting when we calculate that through is 1,882.8 TF minus 10,449.54 equals negative 48.125 TF plus, because we've got a negative negative, so this is plus 4745. So don't forget, here you have that negative, negative, and that's what makes that one positive. Okay. And all right, so now let's take a look at this. So first of all, we have to combine like terms. And so we're going to add 48.125 TF to both sides. And don't round anything early. That cancels that here. Don't round until the end or you won't get the right answer. Okay. And then you're going to add 10,449.54 to both sides. This is just a little algebra review going on here. Okay. And that cancels this part out here. Okay. All right. And now with that, we can put all this together and you will find TF is equal to 7.87 degrees Celsius. Okay. And I didn't do the last part of the math, but make sure that you sit down and you go through that and that you are getting the same TF that I got just now. Okay. All right. Let's take a look at our next one. All right. Here we are on slide 16. All right, so here we have a couple little extra things here, and let's take a look at them. So first of all, we have 250 grams of warm water at 78 degrees Celsius. We have a piece of gold. Okay, so let me go ahead and I'm going to change my colors a little bit here. We have a piece of gold at 2.3 degrees Celsius that's placed in the water. The final temperature that we're going to get out of this is 76.9. So this is TF. Okay. And what we want to know is what's the mass of the gold? So you can solve for some different things here. And they're giving us 4.184 joules per gram degree Celsius for the water and 0.129 for the gold. So let's go ahead and set this up. We have Q of our water is equal to the negative Q of our gold. And so we'll start with the mass of each one. So we have 250 grams of water, and we have an unknown M value. That's what we're looking for our gold. Okay, and then we have our specific heat and water. That's 4.184. Okay, and for gold, that's 0.129. And now they give us a T final right here. So our delta T for water is 76.9 minus 78. So you can see we're not changing very much there. And then for our gold, our final is that 76.9, and our initial is 2.3. Okay, so now it's a little bit easier because we only have this one variable right here. Okay, all right. So now what this ends up being is that on this side of the equation, we get negative 1150.6 equals, and we bring all this together and we'll get negative 9.6234 MAU. And we solve for the mass of our gold, and we get 119.6. Okay. And that's grams. All right. We technically only have three significant figures, so you could round this to 120. But I don't worry too much about significant figures in this chapter. I just don't want you rounding too much. That's really the big thing. And again, for this problem, pause the video and work the calculations on your own and make sure that you are getting the same value for your mass here. Let's take a look now at enthalpy. Okay. And we're learning a couple of things here. Okay. So first of all, let's take a look at what this is going to be. So first of all, enthalpy or delta H is heat flow under conditions of constant pressure. And we're going to be working all of this under constant pressure, which means that we can basically just say that delta H is equal to Q. Okay, so now the things to remember here is that when a system releases heat, the process is exothermic. That means that our delta H value is less than 0 because the heat has left, and the sign on delta H is negative. Okay, so again, an exothermic reaction is any reaction that produces or heat. Okay, so an exothermic reaction produces or gives off heat. And again, that's one of the things that we will be doing in the lab. All right, now next here, we have a system absorbing heat. And so that process is what we call endothermic. In this case, our delta H value is greater than 0 and the sign is positive. So remember that an endothermic reaction is a reaction that requires heat. And in an endothermic reaction, the reaction will never take place if you don't give it heat. So that's a really big thing with that right there. Okay. All right, so let's take a look at a little bit more of this. Okay. And all right, so a little bit more in detail here. Okay, so an exothermic reaction is one that produces heat. And some examples of that is basically anything where we're burning. Okay, because the whole point of it is to give off heat. Another example, or burning, another word for burning is combustion. Combustion reactions are always exothermic. And this is a reaction from the lab that we did, our chemical reactions lab. We'll also be doing it in this lab. And it's that magnesium metal plus aqueous hydrochloric acid, okay, forms magnesium chloride and hydrogen gas. And it gives off a lot of heat. It gets very hot. Okay. All right. And then some good examples of endothermic reactions might be often cooking. I like to use baking a cake. There are a lot of reactions. Remember when we did the lab for R and we needed the Bunsen burner? That was an endothermic reaction as well. Okay, so there's some examples for that. All right. We'll just do a couple more and then we'll take a break on this video. Okay, so let's take a look at phase changes now. Okay, so this is our delta H value for phase changes. And delta H, or again, your change in enthalpy is always compound specific, and these will also be constants that you're given. Heat flow can be calculated using a substance N. Okay, so remember, N is always in moles, times the change in enthalpy of our phase change. Okay, so here we have fusion. Okay, and then we have another way to look at fusion is melting. This is a melting point, a freezing point, okay, depending on which direction you're going on, and then vaporization and condensation, okay. And so basically when we're melting, we require, so this is endothermic, okay, so when we're melting, we require 6,009.5 joules per mole, and when we're freezing, it's negative, so this is exothermic, which means that we release, so we're releasing this energy. and we are absorbing this energy. Okay. And the same thing here. Then this is endothermic, and we're absorbing it because our delta H value is positive. And in this case, we're exothermic, and we're releasing this energy because, again, our delta H value is negative. So that's what those signs mean. That's why they are so important. Another word, vaporization. So fusion or melting. One might be vaporization or boiling. Talk about that boiling point. Okay. So just some different ways to describe that. All right. Now let's look at this slide and then we will go ahead and be done. All right. Not done, but ready for a break. Okay. So let's look at delta H for phase changes specifically. Okay. This is the heat curve for 500 grams of ice from -50 to 20 degrees. And it says to calculate the enthalpy change when 245 grams of ice melts. Okay, so real quick, when we're looking at this, let's look at the fact that if we're moving in this direction, we are endothermic. Okay. And if we are moving backwards, we are exothermic. So if our ice is melting, and so on the bottom, this would be freezing. Okay. So if our ice is melting, we're endothermic because that's the direction in which we're moving. Okay. So we know that that means that we are going to have a delta H value that is positive because it's an endothermic change. Okay. So first of all, we'll start with a step one. And in our step one, we have to convert to moles because our values from the previous slide were for moles. So we always have to kind of pay attention to what our units are. So again, we start out with that. We have 245 grams of H2O solid, okay, times molar mass doesn't change. This is 18.015 grams of water per mole. Okay. And so that means that we will have 13.6 grams of solid water or ice. Okay. And now in our step two that we have here, we need to convert this. This is a simple conversion, but remember from the previous slide, we had delta H is equal to N delta H phase change. Okay. And so we use did not pay here. Let's do that. See, we end in moles here. Okay. And so this is moles. Okay. So this becomes 13.6 moles times a positive, because that's the direction in which we're moving, 6,009.5, and that's joules per mole. Okay. And that's why we needed the moles, because now you can see that that cancels out and we're left with just joules. Okay. And now what we'll get here is 81727.8 joules. We can only have three significant figures here, and this is pretty big. So this would become 81.7 kilojoules. And that's probably how you would report that. Okay. All right. I think that is a great place for a break. The rest of the chapter will be in the next recording.